Welcome. This video is going to look at thermochemical equations and how to use these to calculate the standard enthalpy changes for some common reactions. Thermochemical equations express the amount of heat released or absorbed by chemical equations. So it's very similar to a balanced chemical equation, except you have to be sure to include the physical state of each reactant and product, as well as the energy change, which is abbreviated as delta H, and then the subscript can be reaction or can be more specific to the type of reaction. And delta H, or the enthalpy change, can be a positive value if it's endothermic or a negative value if it's exothermic. Or the value can be included as a reactant on when it's endothermic, it's just the energy value is given as a reactant, or a product when it's exothermic. Standard enthalpy values are the enthalpy change in a system when 1 mole of matter is transformed under standard conditions. And remember, standard conditions are 1 atmosphere and 273 Kelvin or 0 degrees Celsius. So many common reactions or physical processes have known enthalpy changes, just meaning that somebody's actually measured them in the laboratory and scientists have agreed on them. So you can find tables with known enthalpy values for heats of formation for many things, and that's the energy to make 1 mole of a compound from the individual elements, or the heat of combustion, the energy released when burning 1 mole of the fuel. Heat of vaporization is actually a physical process when you vaporize 1 mole of liquid to a gas, and heat of fusion is the energy to melt 1 mole of solid into a liquid. You notice that the 0 is used along with the enthalpy symbol there, delta H, and then there's a little 0, and that's to show standard conditions were used. And then, as I said, the subscript can just say reaction, or it could say formation, FORM, or COMB to let you know it's the combustion, or vaporization, or fusion. So oftentimes that subscript gives you an idea of what kind of process or reaction was taking place. So why do we care about standard enthalpy values? Well, heat of combustion values are commonly used to calculate calories in food or the energy in fuel sources like coal or gasoline or even hydrogen to power spacecraft. It also explains why you cool down as sweat evaporates from your skin. You can actually calculate how much cooling you could expect. And we can use these values along with the MCAT equation to calculate the heat or energy needed to melt or vaporize a substance, or again to calculate the energy released by burning a fuel. So let's look at a few examples. If 54 grams of glucose is completely burned in a calorimeter according to the equation below, how much heat should be released? Now, first of all, I know it's heat being released because delta H is given as a negative value. You know, it just says kilojoules. It doesn't say kilojoules per mole. That's because there's not 1 mole of every reactant and product used here. Okay, but in the case of glucose, it is just 1 mole. So the equation is actually much simpler than it looks. My starting point is I need to change my 54 grams into moles, because my delta H is kilojoules, is given in kilojoules per 1 mole of glucose according to this equation. So in my third try, I've got a slightly different problem for you. I've got 4 equations here, balanced equations, and I want you to decide if each of the following are endothermic or exothermic. So the first one is perhaps the most difficult. If you look at this, you're starting with Fe2O3 as a solid, and it's breaking back apart into Fe solid and O2 gas. So the question is that endothermic or exothermic? Well, we've kind of got we've got a decomposition reaction going on here, which is the opposite of the synthesis. And synthesis or formation is going to require energy being released, because my product is going to be more stable or have less energy than the individual reactants were. So if that's exothermic, then I can expect the reverse equation to be endothermic. And in fact, this reversed reaction, when you have iron combined with oxygen, that's what's in those little hand warmers that people like to use when it's cold out. My second equation shows methane, CH4, combining with O2 to produce CO2 and H2O. So this is clearly a combustion reaction, and combustion is always exothermic. And my last two both involve water in its liquid state, and the first equation shows water becoming a gas, and the second one shows it becoming a solid. Well, if you think about this, liquid water becoming a gas is vaporization, and that's going to require energy, so that's endothermic. Whereas water becoming a solid requires a decrease in temperature or a loss of energy, so that's going to be exothermic.